Okay, so okay, I was talking about this Navier-Stokes equations, and so there are different representations of the same equation. So that's why the governing equations become uh, we are using a different methods, numerical methods for all those different CFD equations. So that's where it becomes critical. And also, it's not just the Navier-Stokes equation. We do some kind of dynamical approximation. For example, the Euler equation, which doesn't use the shear stress term, is also solved under CFD, and sometimes the potential equations. So a lot of different kinds of equation can be derived with the different approximations. So all of them can be classified into CFD methods as long as we solve them in a numerical way. So that's why it is defined that in this manner. And so what are the numerical methods were used? There are many methods available and are being used earlier. And nowadays it is mostly like finite volume method. That's what is used on many commercial softwares, and it becomes a kind of a standard. The finite difference method is what you find in a lot of textbooks as well, and so that is where it started. And in finite difference method, we solve the differential form of this Navier-Stokes equation. And in finite volume or the finite element method, we solve the integral form of these equations, not the differential one. And so the advantage is a lot of advantages are there in the finite volume method, which satisfy the conservations, and we can capture the shocks exactly. And the finite element method is it's also have a good high resolution and accuracy, but there were some difficulties in the shocks where the discontinuities are present. But nowadays, the finite element is also improved a lot after the discontinuous method. Same. The lattice-Boltzmann method is the one which uses a particle concept of kinetic theory. So the kinetic theory of gases might know, and they try to solve the collision of the particles and get the solution. It's completely a different approach, the lattice-Boltzmann method, which is also a kind of solving the Navier-Stokes equation, but not the direct one, slightly derived from Navier-Stokes, or a compatible equation of the Navier-Stokes, I would say. It's not derived from the Navier-Stokes, it's derived from the kinetic theory, but it can be related to the Navier-Stokes equation as well. So this is what the CFD in a very, very top level. And can you go next slide? Yeah. So what are the process involved in CFD? So the first step is the geometry. So when you start doing a CFD application work, right, the first thing is the geometry. So we have to develop a geometry, or designer would provide a geometry, and we have to do the cleanup of the geometry. That is, it's quite difficult task, and it consumes a lot of time. And there are a lot of softwares available to do the cleanup. So that is the first step. And the second step is generating a mesh. So if you see here, it's a surface mesh. So we will generate a volumetric mesh also. The mesh generation is the second step. And there is, I've seen with the people, there is a lot of confusion between the mesh generation and the discretization. The discretization is something different than the mesh generation. The purpose of mesh generation is that whatever the equations we saw in the previous slide, those equations are continuous. So we are trying to solve a differential equation and the integral equation. They are continuous in nature. And those equations are valid within these small control volumes or the mesh. And from one mesh to other mesh, there could be a discontinuity, or it could be different. And this is called the weak solution. So that is the primary purpose of generating the mesh. And the third step is, after generating the mesh, the third step is the initial and the boundary conditions. Okay. So where Shruti, can you move to the, or you just, yeah, or just you put the full slide also with us. Okay. Yeah. And the initial and the boundary condition is the next step, where we try to define the boundary condition of the problem. The boundary condition is very important because most of the times we don't solve the complete actual cases as it is. So we try to restrict the domain of interest, and whatever the boundaries of the domain, we have to do some approximation and give the values there. And that approximation should be reasonable, and that should able to capture the physics. So most of the times, if the CFD solution is not converging, has some issues, it could be the relation, the problem with the boundary conditions or meshes sometimes. And the initial condition is critical for some cases, and most of the problems we solve is initial condition independent, and so it's not very critical for the final solution, but it influences the convergence rate. So if it's converging faster or slower, taking a lot of iteration, it depends on the initial condition. Sometimes it could diverge because of bad initial conditions as well. The fourth step is the model setup. So model setup is setting up the model like numerical models or other physical models. For example, if you're solving your combustion model, then you have to set up the chemical kinetics. So those kind of things. And so once you set up the models, the numerical, there are a lot of numerical parameters out there, turbulence models, and so many are there. So once we start learning the CFD, then you will understand that so many tuning parameters or setting parameters are available. So those things we need to set up to get the efficient and accurate results. And the final one is the solution. The solution is the easiest job a person can do. Submit the job in the cluster and just wait for the solution to converge. If it doesn't converge, go back and fix. So that's where the CFD engineer becomes, the knowledge of CFD becomes important. It doesn't converge the first time. So we have to go back and understand what is the real problem and where we miss, whether we are missing the physics or numerics or something else is the real issue, and go back and fix that one and make sure it converges and develop some understanding and standardization of what we are doing. So after the solution, the next step is the post-processing. Can you go to the next one? So there's a post-processing. Yeah. So the the post-processing is the real analysis as an engineering work. People do the analysis, and a lot of engineers spend a lot of time on the analysis part, the designers, which actually gives the solution to the problem. The different kind of post-processing. Most of the time, CFD means people will see only the field data, the colorful picture as shown on the aircraft, the green color one, the bottom left. That's where people think CFD means it's just a colorful plots. Many people have that in their mind. It's not just the field data what you are interested in. We are solving the problem at each and every control volume. And we also get the integrated solution, like the overall lift, for example, the overall lift for this aircraft, or the overall drag, or some pitching moment, or the pressure distribution on the particular section of the airfoil, which is shown here on curves, that gives the pressure distribution of the wing. So we can get any kind of information we need from the post-processing. So that is the real advantage of the CFD. So can you go to the next one? Yes. So here are the pros and cons of CFD. So what are the advantages of the CFD? So few things is quite obvious. Less cost, less turnover time relative to the experiment, and no need of scaling. This is a quite important advantage. When we're going for a scaling, we have to make sure it should be geometrically similar, kinematic, dynamic similarity, and we know that most of the time we cannot achieve all the similarity parameters. It's very difficult to achieve, and you have to do some compromise, do some correction after doing the testing. So all those things. So in CFD, there's no such need. So we can directly do the on the exact scale and we can get the exact result. The comprehensive information, what I explained in the post-processing, we can get almost any kind of data we need from the CFD result. And the next one is how to test problem. Some problems are very difficult to test practically. For example, in aerospace, some high altitude, so the flight goes in the high altitude. So all those high altitude effects are difficult to test. For example, if you're doing a re-entry vehicle, so those heat transfers are very difficult to test the actual scenario of what is happening at those Mach numbers. Some of them we have to do some shock tubes or some kind of test. That is difficult. So in each industry, there were some kind of problems are really difficult to test, and those can be easily solved with the CFD. And the next one is the large design space. This is the parametric space where we can do the design. With testing, it's almost limited, but we are limited by the setup itself, sometimes cost, program time schedule, so many things will limit the design space. But in CFD, we can explore much more. And it can also be used for the concept selection without spending a lot of money, so the cost effective. And most important thing is understanding trends. So if you want to do certain experiment, so then we can understand whether a particular variable has really an impact on your field of interest or the interest. If you found the CFD says it's not having a strong correlation or it's not of important, then probably you need not to spend time in testing those parameters in the experiment. So it is really useful in many things. Like it just gives the trends, whether it's going to increase or decrease or remain same. So all those correlation effects we can able to estimate from the CFD. And the disadvantages, the cons of the CFD is, Shruti, can you go to the next one? Yes, okay. The main drawback is it needs a validation. You cannot trust the data or the results just like that. So it needs to be validated before using any model. There should be a validation should be done. Otherwise, no engineer will trust the results directly. So that is the real drawback of the CFD. And the other one is the simplified geometry. So most of the times we end up in simplifying the geometry because of the meshing requirements or some other reasons. So we don't try to model the complete geometry. So we have to simplify the geometry. That will have some impact. And also the mesh itself is a simplification of geometry. So for example, if you want to capture the curvature, then you have to put a lot of meshes, and so those kind of things are there. So the mesh usually makes the curvature flat. So there is some approximation, but usually we try to capture that by putting the more number of cells. So it's not a critical one, but that is one of the disadvantages that we have to keep in mind. And the simplified boundary condition is the other one. So we cannot simulate the exact real physical boundary conditions. Sometimes we don't know those boundary conditions. Sometimes it's very difficult to model that one. So we have to do some approximation there and understand its impact. And simplified models is like you want to model, for example, acoustics model. We don't model exactly or solve exactly the equation. We use some models to understand the impact of aeroacoustics or fluid acoustics or the combustion models, or even the turbulence models are very much simplified. There is no direct closure that's available. So those model simplifications will have an impact on the accuracy of the solution. The final one is the computational time. So this one could be conflicting. So I put less time, less as both advantage, and here the computational time. So it's not suitable for all the problems, but in some problems, the computational time becomes mostly unsteady problems and the problems where you need a very accurate data. So people tend to use a LDS kind of simulation. The computational time for solving one case can take almost a month or even more than that. So by that time, in the organization, a well-established organization, you can already have test facilities or setup almost ready. You just want to build a model, probably using a 3D printing or some other techniques and test the model, which is much more easier option when compared to solving for 1 month time with a lot of computational resources. And at the end of the, we don't know how much accurate is that also. So it becomes sometimes it mainly for unsteady problems, and it could be a drawback. I wouldn't say it is always a drawback. Can you go to the next one? Okay, so this one is talking about the evolution of CFD. So the arrow mark indicates, as mentioned, how the complexity of modeling got increased over time, and the accuracy of the flow physics or the cost. So when the accuracy increases, the cost also increases. And if you see, Shruti, can you just put? I think it's better to put so that I need not to mention every time. So yeah, okay. So the first one is in 60s. If you see, the people try to solve the linear potential equation based on those computational resources available, and they are linear equations. Potential means it's inviscid rotational equations. So what are those methods typically? So most of these methods, some of you might have heard. It's panel method. It's called source panel method or vertex panel method, and vertex lattice methods. A lot of methods are available, and transonic small perturbation equations, integral boundary layer equations. So all those were solved, coupling the panel method with the boundary layer equations. So all those were used in 60s, early 60s. And with time, people started putting the non-linearity effect into it and trying to solve that more kind of iterative kind of problems, where the full potential equation is solved, and with shock fitting techniques, finite difference method was got evolved, and finite difference method got used into CFD. So there is a right statement, and people started using the convergence acceleration techniques like multigrid. And so all this are for the compressible flows. At the same time, for the incompressible flows, the pressure correction techniques like the simple algorithm came into existence. So those uses the staggered mesh initially, and then it moved into co-location methods, which happened during the 80s. The finite volume method came into picture. With the finite volume method, we could do the shock capturing. That is the advantage of the finite volume method. And started using the higher order methods. Limiters came into existence, row schemes, other lot of numerical schemes came into existence, flux calculation schemes, and also on the meshing side, people moved from single block meshes to multi-block meshes and co-location methods. So all those things came. In 90s, it's like RANs. That's where the real commercial CFD started. RANs and unstructured meshes, OSET meshes. So most of the things what we are using now, it's all from the 90s and beyond that. And after 2000, the CFD methods have not undergone a rapid growth as happened from 60s to 90s. After that, it is almost a kind of plateau, but a lot of different things came into picture. The wide application of the CFD started after 2000. So if you see the LES, DNS, so all those things came, and a lot of models like particle interaction model, moving boundary measures, multi-phase. So many things came into existence, different model aspects after 2000. And on the numerical side, if you see the agile methods came. This agile method is still available in the commercial purpose. So some of the industries were attempting to use that. It's optimization technique based on the native stroke. And polyhedral meshes were already available in a lot of commercial software, which is the evolution of the structured mesh. And a lot of research are going on in the meshless methods as well. Probably in some future, we may end up with the meshless method. And LES, some industries started using that. DNS is still distance for. And the interesting one is the GPU. This is purely on the programming side. So people started using CPU computations to the graphical processing unit. And so that gives a lot of speed advantage in the solution. And the finite volume methods started evolving with discontinued years. So it gives a very good accurate numerical schemes. And the lattice Boltzmann method came into existence recently, and even it got industrialized and people started using in the industries. So those kind of FSI is the fluid structure interaction problems, like the flutter and buffeting kind of problems started using the CFD. Can you go to the next one? So next one is, I think, the application part of it. So I'll bring the full slide. So on the industrial applications, a lot of industries uses the CFD. As shown here, aerospace. It all started with the aerospace industry and automotive construction. The construction industry is like the bridges, okay, and the high-rise buildings started using estimating the wind loads on those things. So there is one video, probably interested people can look into that. At Tacoma Bridge, you can search that. So that bridge got collapsed because of the excitation from the fluid dynamics. So that has given a lot of interest in those kind of civil structures, and a lot of other civil structures uses the CFD applications. And energy industries is the gas turbine, the wind turbine. So even the solar panels, the loading from solar panels, nuclear energy. So almost all the energy companies use the CFD. And the marine is the obvious one, the shipbuilding, marine, and other marine applications, and chemical and process industries where optimize the pipings, routes, and the heat exchangers. So those kind of things. So almost all the industries. Can you go to the next one quickly? Yeah. And one more, please. Yeah. So almost many industries, like medical industries, it's growing. Actually, the medical industry application in the medical industry started growing, mainly in the blood flow, the cardiac. A lot of research in the cardiac area is happening. The biomedical and pharma industries also using CFDs for their processes. And also a lot of research are going on the targeted medicine. So how the medicine is carried on the bloodstream and the targeted infected area. So those kind of things are happening. Electrical and electronics, it's almost become, I think it's almost established now. Many electrical and electronics were using CFD, like a lot of electronics coolings, electrical coolings, motors, so cooling for the motors, electrical panels. So almost it is there. It's a well-established one. And industrial equipment is the other one, like blowers, pumps, boilers. So many of those design and optimization, those were using the CFD. Sports industries were also using that one. Like race car is the one which is quite famous, and it also is being used in the other, like cycling, swimming, so many different to train the sports person, and so it started being used in there. The manufacturing industry is a relatively new one, like the casting process, additive manufacturing, flow forming. So those kind of with phase transitions, right? So even those kind of models can be done with CFD, and manufacturing industries, some of the industries have started doing that one. For example, the electronics manufacturing uses the CFD for quite some time, and the other manufacturing were also started using that. So environmental is something like HVAC. So it's typical problem in the HVAC is CFD usage in the HVAC is quite heavy. Almost all the HVAC companies use the CFD, and also in weather prediction, climate predictions. So all those industries. So there are almost all industries, most of the industries, I would say, some of them are not listed here, started using CFD. Maybe in future, after 10 or 20 years, you will see more and more industries start using CFD, and it will become the part of their process. So the next slide, I have shown. So what kind of application? So if the industry is using what kind of application, there are multiple applications and models they use. This is just one example. For example, in the automotive, I put some 4 applications. There are much more there, like combustion. So all are very different problems in terms of CFD, but used on the same industry or the same product. So the engine, so which is a moving boundary problem, that the piston moves and combustion happens. So it's a combustion we are trying to solve the moving boundary problem. It's a very complicated modeling. If you see the turbocharger, on the other hand, we don't model the complete turbocharger. We just model only the one blade with the periodic boundaries. So one blade with periodic boundaries, and just a minute. So what happened? Oh. Yeah. Sorry for that. Suddenly the application got disappeared. Where we use the periodic boundaries and solve something called multi-reference frame. So we don't actually move the boundary or the geometry or the measures. It's all solved with stationary coordinates, but we change the equation and add those pseudo forces like centrifugal and Coriolis forces and try to mimic the effect. And so there will be like a relative frame of reference or stationary frame of reference, a completely different approach of problem. External aerodynamics, where the gross forces are the primary importance. Here it can be used for the stability of the vehicles. So those kind of applications, and the heat transfer applications on the underhood. So that is the one, and something like we can solve multi-phase flows and the tank flushing problem, or HVAC. So even in the automotive passenger comfortness, HVAC becomes important zone of the application. So it's not that a particular industry uses a particular approach. So for example, the combustion is used in many industries. So if you know combustion modeling, then you can fit in many industries, something like that. So different models or cut across the industry. So that is the advantage of knowing CFD. Can you go to the next one? Okay, so this is the job opportunity part, and as I told earlier, CFD is when I was doing, or like 15 years back when I joined for a job, CFD is not something that it's kind of, if I know its advantage, if I don't know, nobody cares actually, at least in the product industries. So that was the situation, but nowadays it's not like that. So CFD has become an integral part of the process, and you have to know CFD somehow, or even if you don't know, you will be learned within first couple of months once you enter any company. So it becomes a mandatory now. So there is no escape from CFD if you are employed in a fluid dynamic related job. It's something like become like the finite element method for a stress analysis, right? If you want to go in a stress analysis or structures job, it becomes a mandatory. So there is no escape from that one. CFD has become something similar in the fluid dynamics in the heat transfer area. And so without knowing CFD, this actually becomes a drawback. So that is the kind of situation we are going into and what's happening in the current industry. So if you look into the job opportunities, what kind of job? Can you go to the next one? What kind of job we can land, or what kind of roles we can go in? So typically, from my experience and observation, what I see, we can land in 3 kinds of roles if we are good in CFD. Okay, the first one is a developer role. It's purely used by the CFD industry, like Answers, Siemens, a lot of CFD solvers are like COMSOL, and so many solvers are very in the OpenFOAM, ESI. So if you want to go and develop the solver itself, it's a developer role. That is one of the roles, and where the programming I put high. So there is people can debate on those things, but just from my experience, I have put this one. So it's not that, it not mean that the others are not less important. At least from start, from nothing, if you say, right. So if you're good in programming and know a little bit on the numerics and model physics, probably you can, for a developer role, that is good to start with. But that's not sufficient. You have to learn a lot after some time, maybe a year or so. And the engineering knowledge is not very important actually for a developer. So that is how it is. And if we go on the support role, it can be 2 kinds. One is you could be in a software development industry. I mean the CFD software development industry, where you are supporting the developers and the application. It's called application engineer, and you are supporting the customers. So those kind of roles. Or you are in a product industry, OEM, and there you could be in a methods role, where you develop methods for doing the product development. So both of the roles, the model physics is very important. It will be more focused on how good we are modeling the physics, or we are getting the results, how accurate, how to do that. And numerics becomes important, and programming is also important in the next level. But the programming is not as same as what developer does. It's more like a user-defined program, supportive programming. That's what we have to do as a application engineer. And engineering, it's okay to have, but being a support, it's better to have equivalent, almost equivalent knowledge in the engineering as well. Though I put low, it should not be low. It should be like close to medium, medium side of low, I would say. And the other role is the design or the functional role, where you are a product working on the product, and so where the engineering becomes a predominant, very high importance. But you, as a part of multiple tools like experimental or analytical or some other low fidelity tools, you have to use CFD as part of your tool. And most likely nowadays the functional role, the CFD usages could be as close as 50% or even more. So in that case, we have to put in solving the model physics and numerics, and programming. It's of low priority. Most of the people doesn't know programming, in fact, but it's good to know some programming for any engineer, I would say. So these are the kind of roles a CFD engineer can take. Can you go to the next one? Yeah. So this is the last slide, and so here I'm going to, how do you start a career in CFD? First, if you don't know anything on the CFD, it's okay. Do some introductory courses which could cover the fundamental aspects of the flow, numerical methods, and how the flow model and the numerical methods are linked. So that is the basic understanding a person should have, and some amount of programming, basic programming is required. So that is the where one can start with. And the two aspects to learn, one is on the programming side. If you are more interested as a developer, then you have to do little more on the programming and start writing some 1D codes or something to understand what is happening. Or if you are more interested on the application side, you have to start learning some softwares, try to solve the problems. So this is how it helps. And this particular course is trying to put a balance on the both side, and so that it just creates a fundamental platform, and then after this you can decide kind of where you want to focus more. So that is the idea. And can you go to the next one? Yeah. So what are the prerequisites for this one? Okay. So my plan is that to cover some aspects of the important mathematics in this one. So if you have a understanding of the UG level mathematics, okay, and fluid mechanics are the one is important here. And during the course, I'm trying to explain those aspects as well. So you should have some understanding on those elements and able to understand the concepts explained in those terms. So that is a prerequisite. And programming knowledge is not really necessary to start with, but definitely after starting, you have to learn programming. So there's no escape from that one. But to start with, there is no such. Don't worry if you don't know any programming. And the most important is a passion and dedication. So that's very, very important for learning anything, and particularly in CFD, which is you have seen it's kind of a multidisciplinary it cut across the mathematics, computer programming, fluid mechanics. So you might get lost somewhere, and so unless the passion and dedication should be there to drive to reach your goal. Yeah, so I think that's all I want to cover on this one, and probably if you have any questions, then I can answer this.
Thank you so much, Anand, for walking the students an informative session. So participants, we have been receiving your questions. You can feel free to drop your questions even now. So Anand, the first question for the day is lattice-Boltzmann method is equal to boundary element method?
Okay. So the boundary element method is completely different. Okay, so the boundary element method is the so no, there is nothing on the slide, I think so. It's okay if you don't go back. So the boundary element method is completely different. In boundary element method, we solve the Navier-Stokes equation, but how the boundary is modeled is what different. And there are multiple ways of boundary element methods are available. And so that's the real difference is how do we model the boundary, the wall condition, and what kind of approximation we use. So that is what the boundary element method is. And in case of lattice Boltzmann, is completely different. It's more like I wouldn't say Lagrangian, but it's something like we solve like a particle. Okay, solve in terms of particle, like a fluid particle. You are injecting the fluid particle and try to see how they collide and how it moves around. And it's completely different approach. Okay, so it just uses a kinetic theory, and we apply a distribution of particles and see how the particle collides and the resulting force where it moves, and so from there we try to estimate the field data. So that is the lattice Boltzmann method, where we use it's called lattice, and it's not a volume, and try to solve the problem. So if you need more information, right, on these things, it's so the concepts are quite different, that I would say, but exactly if you want more information, then probably we can maybe when we have more touch time, we can look into that.
The next question for the day is, what are the programming? So, are there any programming knowledge required for the CFD domain?
Yeah, yeah, definitely it is required if you want to go into the developer role. But if you are in as a product engineer want to use the CFD, maybe it is not that much, or may not be required also. So, but it's good to have the programming knowledge. And to start with, if you want to start learning, yeah, we have to do some primer on the programming and get some understanding. But it depends on how much. For example, if you are a developer, you should have a proper programming knowledge. You should know the data structures, algorithms, those kind of concepts. If you're doing some kind of very basic level, then not much like MATLAB or Python is sufficient enough. You need to focus much on the programming aspect. Just do some quick coding and get the results of what you want to do. So that is the level, I would say. So it depends on the role what you are interested in.
Thank you so much, Dayanand. So the next question for the day is, how CFD will impact research in the near and far future?
Okay, so CFD is already impacting the research. Okay, so here I'm not clear what kind of research you are talking about. The CFD itself has its own research, first thing, and so a lot of people are doing research on the CFD itself, how to develop a better model and how to improve the speed of convergence or accelerate the or how to solve in less number of iterations. So a lot of research are going in the CFD field itself. Okay, and if you see how to use CFD for the research, it is almost there already. So people started using CFD for research. So if you want to, for example, whenever you want to do a particular concept, understand a concept, the first thing is people don't go for testing. So those period is over, I think. So the first thing people try to model in CFD, if you want to do certain, understand some particular phenomena, or if you're designing some vehicle and see how much what you can achieve or what can be done on that one. For example, if you're designing a gas turbine blade, and if you want to see how the heat transfer, if you want to do some research on the cooling methods and how to cool different cooling holes, all those things, right? So people use CFD at the first cut analysis, understand what happens, and then try to do an experiment and see what is happening. So CFD goes hand in hand with the research. It's not the experimental, the need of experiment is always there, because that is the final proof or the validation. But the percentage of experiments that used for research is going down drastically, and the CFD is started dominating that one. Already it's started dominating. So that's that's the current status, and the future it will remain same. The experiment, we cannot get eliminate of an experiment, so it has to be there. But most of the times we try to design the experiments based on the CFD data, and that's what we are already doing in many fields.
Thank you, Raymond. The next question for the day is, why should we use OpenFOAM instead of Answers Fluent?
Okay, there is no particular reason for using that. OpenFOAM is free to use. It's GNU license, I think it's called. So it means that you can free to use even for commercial purpose. Okay, and the cost is the advantage. So if you're going for Fluent, it's extremely costly. Okay, and the advantage is that you will get a lot of support on the fluent, so the answers will support you. That's the only reason. If you're worried about the cost, OpenFOAM is the way. If you have a lot of money to spend, answers, they can go for answers. The relatively, if you see what are the models available, also there are some differences in the models, and the validation effort that put on the OpenFOAM and the answers are quite different because it's an organization and it's an industry answers, and so a lot of validation has been done, and a lot of models are being developed. In OpenFOAM, we have a lot of models. So if a particular problem what you're trying to solve available in both, then the cost and the or your comfortness and the software. So all these factors drives you to select. And the primary, I think it's the cost, which drives the selection of software.
Thank you, Dr. Anand. The next question for the day is, what are the current challenges of CFD in the field of electric vehicles?
Okay. So, sorry, before that. So, for electric vehicles, the CFD, okay, so the electric vehicle, apart from the engine, right? So here we are using the battery and the motor. So what I see, I don't have a direct exposure on the electric vehicles, but what I could infer from my understanding is that the heat transfer is the very critical one for the electric. The motor cooling and the battery cooling is very critical, and that's where the CFD will contribute in the electric vehicle. And there are some areas where people are trying to model the batteries in CFD. I don't know exactly where how they use, but a lot of battery process, the diffusion process inside the chemical process inside the batteries were also modeled in CFD. And so I think these two are the major one. And a lot of fuel cells are coming. If fuel cells comes, then the CFD in the fuel cells also becomes the other area. Other than this, the other features of automobile between the electric and the conventional, gasoline one, are same, like exterior aerodynamic stability. So all those things are quite common. So those remain same. The hatchback, the passenger comfortness. So those elements remain same between both the vehicles.
Thank you so much, Dr. Anand. And the last and final question for the day is, we have a bunch of students who are from different backgrounds. So when it comes to CFD domain, what are your thoughts on the scope in the upcoming years? And how can a fresher start his career in the CFD domain? And if he starts, what will be his growth as a CFD engineer?
Okay, so can you repeat the first one? Is what? Can you repeat the question? I think there are multiple questions in that second question.
So the part one of the question is, what are your thoughts on the scope of CFD in the upcoming years?
Okay, so as I already explained in the presentation, the scope of CFD is going to increase a lot, and it's going to wide in almost all the industries. So many industries started realizing the importance of CFD because the products are getting more and more matured, and quality of the products are getting improved every day, and the productivity and the efficiency of the product has to increase every day because of the higher competition. So all these are driving to a niche design or very effective design which demands CFD. So that's where the industry started focusing to get a competitive advantage. So all the industry which focus on the growth and the competitive advantage, those companies started using the CFDs. And the CFD is still not reachable in the mid scale and the small scale industries because CFD is also very expensive. And the commercial CFDs, particularly as one person asked the OpenFOAM answers. If for a company like like a big companies, for example, a company like Boeing or Airbus. So these kind of companies, a lot of money they can spend a lot, and on the commercial codes and many automobile industries. And if you go into the small scale industries, that's where commercial codes are really expensive. Once you started using, you'll learn how, or you'll come to know how much is the license cost per year for different softwares. And the OpenFOAM kind of softwares were used in those industries which could not really spend that much money. Okay, so and because of these softwares, also the scopes are getting increased every day, and many industries have started using, and it also goes into a different kind of industry. For example, manufacturing industries were not into CFD, and now they have started using. The biomedical have started using the CFDs. So lot of such things. There's electronic schoolings now with the. If you see a lot of job profiles in Intel and other electrical panel manufacturers, like where they were asking particularly the CFD engineers, right? So for a chip manufacturer, the CFD, nobody has thought about CFD need on a chip manufacturer like 20 years back, but now it becomes it becomes a part of their process and the rules, and so that it's growing, and I think in future there are much more potential industries that can adapt CFD. So with the time it's going to go up, the scope is going to increase. And I think the next question is how to start the career, right?
Yes.
So to start the career, as I already told, you have to start somewhere. Okay, so the first step what you have to take. So don't worry about how to start a career. Just do some course, some learn the books, and so if you have access to any commercial software, try to use the commercial software or OpenFOAM. So you have to do something, and once you start working on that, you'll know that so many things are there to understand and learn. Go and read and take some courses if you want a rapid acceleration to start. If you have a lot of free time, then you can do it slowly by yourself. But if you want to accelerate and learn quickly, then take some course, get trained by solving the problems. So that is the way actually. So there is no different or special techniques for that. So you have to mix your hand dirty. So that is the only way to learn anything.
Thank you, Dharanand. Thank you so much for patiently answering all the questions from the participants. And I guess I covered most of the repeated questions which were asked from them. So, Dharanand, before we wrap up today's webinar, right, do you have any other things which you wanted to share to the participants?
Okay, so probably I can. So all of you guys are very much interested in CFD, right? So that's why you are attending the course and trying to learn the CFD, which is really good. And learning a skill is really important, at least in the initial part of the career. Once you put the CFD in your resume, then it's going to attract. And also when you're doing the CFD, right, you select the problem what you're solving by targeting the right industry. And so add those kind of problem, the resume will give a lot of value addition. And also it is very, very important to know the fundamentals of CFD, the very basic aspects of CFD to crack any interview. Once you go for the interview, people are going to ask the basic questions, 50%, and that's where the basics becomes very important. And so for that, you have to learn, study a lot. So those are the major things to do. And also try to see if you're already employed in CFD, then you're you are working, then you have to accelerate your learnings in the CFD. So many people, what I have seen in the industry, will move to some job, start doing something, and later it becomes like they start just repeat the CFD process again and again, do the mesh, run the job, do the mesh, run the job, and I'll get the results and do. And then it becomes more like a robotic things, and people start focus on the losing the focus on the knowledge part of it, which is quite bad. And after few years, they feel like they're stuck in the job. They difficult to move out or grow or something like that. So that's why you have to keep on improve your knowledge. Whatever you are doing that, you should know exactly what you are doing and why you are doing. So that's where it becomes very important. And so don't give up the learning. And I think now you are at the right place, and probably it will give you a better, you'll end up in a better opportunity and start learning, and also getting a job or getting a better position in the job. So these kind of learnings and understandings will be very useful in your career. Yeah. So all the best to all, and that's what I want to say. Thank you.